Hello and welcome everybody to our last session of Webinar Week. My name is Brian Tipper. I'm the VP of Sales and Marketing here at OptiWave, and I'll be sitting alongside your host, Scott Newman. This webinar will be the second segment of Advanced Applications for our OptiFDTD software. To start off, I'd like to extend a big thank you to everybody that has been able to attend one or more of these webinar sessions, and I'd like to extend an even bigger thank you to the select few that have managed to attend every single webinar. By this point, everybody knows the drill. We will launch 3 polls during the course of the presentation and have 2 Q&A periods for answering any questions you may have. Lastly, we'll be recording this webinar and emailing the link to everybody tomorrow at 4 p.m. Eastern Standard Time. Let's now get this webinar underway. I'd like to introduce your host, our OptiFDTD project lead, Scott Newman.
Hi, Brian. Thanks for the introduction. And I'm just firing everything up. Perfect. So I'd like to reiterate Brian's appreciation for everybody coming out and actually getting a chance to see, in many cases, multiple webinars. And I'd like to carry on with advanced applications. So instead of taking a look at some of our previous ones have been more tutorial based. What we're going to do today is we're actually going to take a look at slightly more advanced examples and a touch less tutorial style. So what we're going to start with is we're going to start taking a look at a paper that was published in 2007 that took a look at silicon nanowire arrays. And the reason I chose this one for our first approach, the first of the 3 examples we're going to take a look at, is because it actually gives us a chance to take a look at unit cells and an opportunity to potentially do parameter sweeps and material modeling. So what I did when I chose these examples is I kind of took questions that we were getting throughout the week and kind of targeted it that way. So in this particular one, so it's an array of silicon nanowires, and they have a raw diameter of 0.05 microns and lattice spacing 0.1 microns. And there are 3 different designs that range, and they take a look at the rod length. And what they want to do is they want to take a look at the absorption of these designs. So we're going to go ahead and jump right into Designer here. And we're going to fire these up. So instead of modeling an entire array, which is going to require a fairly lengthy FDTD simulation, the plan is to actually take a look at just one rod and use periodic boundary conditions to minimize the amount of simulation time that we actually have to do. So before we get into actually creating a design, we have to go and define our materials. So we double-click on the materials to launch our profile designer, and then we're going to import, here we go, predefined material that I've defined, which is silicon. There we go, advanced. So I've gone ahead and defined, I'll show you how we define these, and exported them, both silicon and silver, for the different examples we'll need today. But I'm going to use the silicon for this one. And you'll see it loads up a silicon material under FDTD dispersive. If we open it up, we see that we've defined the dispersive characteristics of the silicon using the Lorentz-Drude model. These are the coefficients we used for this particular fit. And all I simply did to keep it for future use is I exported it to an XML file so that it could be imported. The other thing we need to do is we need to create a waveguide profile that will characterize the rod that we're going to use. And we do that under Fiber, under Profiles. We create a new fiber, and we're just going to call this rod. And we're going to define, in this case, a 3D profile. So we want it's going to be circular, so we want both the RX, the radius in the X, and the radius in the Y to be the full scale, so we'll leave those as 1, but we are going to change the material to be silicon, and we're going to add that. And that sums up our material setup. Now we come back to our simulation space. So we're going to set up our simulation domain to be able to fit one rod. So we're going to make it a length of 2.4, and the width will be 0.05 microns, because we're actually modeling this quite small. Perfect. And we'll change our simulation space here. Now, we need to go ahead and add our component. And before I do that, I do want to comment on boundary conditions, because I like to think about my boundary conditions when I think about my simulation domain. In this 3D space that we've defined, we have a very narrow X, and it should be a very narrow Y. My apologies. We go back to the simulation domain under 3D wafers. So the way this works is we've defined the Z coordinate, which is the length. We've defined the X coordinate, which is the width. Now we need to look at our 3D wafer properties. And these thicknesses should be 0.025 and 0.025, so that together they're 0.5, and the background should be air. So we define that. There we go. That looks better. We have a very small extent in our X and Y, and then the nice long extent in Z. What we need to do is we need to be able to model an infinite array. So we need to set up our boundary conditions on the plus and the minus Y and the plus and minus X to be periodic. So we're going to go into the 3D simulation space. We're going to go to Advanced, and then we're going to go ahead and switch the boundary conditions to periodic on both the X and Y boundaries. We'll leave the boundary conditions in the propagation direction to be PML. We want those to be absorbing boundary conditions, so we're just going to leave that as it is. So we're going to hit OK, and we'll leave the rest of the simulation. Interesting. Let's try that again. I didn't change any of the numbers. We're just going to switch these to periodic boundary conditions. And okay, so what we're going to do, just in the interest of saving time here, desktop, advanced, and we're just going to open up the pre-built one here. I'm not sure what's going on with those boundary conditions right now. So this is the space that we actually created. You'll see that if I open up the simulation properties, I have set the periodic boundary conditions to on the X and the Y, and then we have the simulation space. Now, what we then go ahead and do is we actually set up the linear waveguide that will define the rod. So we set it up so that horizontally it will start at 0.7, and it's centered in the vertical direction, and on the end it starts at 0.7, but then we add the 1.16 microns, which is what we want the length of this particular rod to be. We'll also go ahead and define the width of it to be 0.05, and we assign the waveguide profile to be the one we defined earlier. So we'll hit OK on that. Then what we do is we add the input plane, which is added by this icon here. And that input plane has a number of things set up for us. The first one is we centered it on 0.35 microns, and we want it to be effectively a plane wave, so we set it to be rectangular, and we define its extent to be right across our simulation space. The other thing that we go ahead and set up is we want multiple frequencies. We want to look at the absorption spectrum on this. So we hit the sine modulated Gaussian pulse. We define the central wavelength so that the center frequency is roughly in the range we want, and then we define our full width half max to give us a nice decent spread across the frequencies. We also define two observation areas. The first one, which is this one here, is defined at 2.1 microns in the z-axis and is given a length of 0.1 in both the x and the y, so it spreads right across the simulation space. And this is an XY area, so it's a slice in the XY. And then that will monitor our transmission. We create a matching one on the reflection side that's located at 0.2. And just for interest, so that I can show a result, we create a observation point at 2.2 microns. Once that's all set up, we go to a 3D simulation. Because our rod is set to a diameter of 0.5, we set up the mesh sizing so that there is 20 points across the radius. So 0.05, 10 of them would be 0.005, 20 of them would be 0.0025. So that's where we figured out the spacing on this. And this spacing here is a bit of a magic number. We play with this one to make sure that the simulation time is run long enough so that the field from the pulse is actually propagated all the way through the simulation space, which is something I will show in a moment. So that is that. I'm not going to run it on here simply because this particular simulation will take a little bit of time. So I'm actually going to open up one that is pre-solved for us. And the reason we created the observation point is because we want to take a look and make sure that the simulation was run long enough so that all of the energy from that pulse has had a chance to propagate. So what we're looking for is we're looking for this dying off of the signal at that observation point, which, if you can see, is located right there. The catch on this one, it wasn't run quite long enough, but from the decay, you can see that it has been run. Most of the signal has gone through, so our information should be adequate. So what we go ahead and do is we want to take a look at those two observation areas. And what we're after specifically is the power spectrum of them. So we're going to take a look at the combined power propagating in the Z. We normalize it to our input plane, and we want to take the absolute value. We would save this. This would be it's observation area 1, so that means this would be our transmission, which is this one here. And then if we take a look at our observation area on the second one, we can get the reflection spectrum for this particular structure. And what you can do is you can save these two, and you can either have a OptiFDTD script that will actually do the math for you, or do MATLAB, or however you want to process the data. And what you're looking for, because we're looking for absorption, you want to find the difference between 1, you want to find the value of 1 minus the reflection minus the transmission. And I've already gone ahead and calculated that for us, which gives us this one here. So on the right, you see the results from the paper. And on the left, I've got the results from 2 of the lengths, the 116 nanometer length, the 1.16 micron, and no, not 1.16 micron. This should be 1160, and this should be 2330 to be our 1.16 microns and our 2.33 microns. My apologies on the legend there. But we see the reproduction of the results from the paper. This is also an opportunity. You could have written a script for changing the lengths of these rods so that you could have one simulation that runs the 3. In this particular case, I ran 3 separate simulations. So that's calculating the absorption of the silicon nanowires. And what we're going to do is we're going to jump right into another example. And what we're going to do is we're going to set this one up, and then we are going to go ahead and go for our second poll before I run the simulation. So I'm going to set it up now. Well, I'll lead into it. So this one here is a plasmonic simulation. We had a number of questions in the previous webinars asking if we could do plasmonics, so we decided to take a look at one that looks at surface plasmon polaritons. So in this particular one, the background is set up to be silver. That's this blue area from this paper. And the actual waveguide, or the channel, is filled with air, and you're actually getting propagation along that interface between the air and the metal. So we're going to go ahead and take a look at that. The other thing I want to be able to show is a really interesting opportunity to take a look at parameter sweeps. So we're going to do that. So this is the actual structure we're going to define. It's just a waveguide with this tooth, and then the background is going to be silver. So we're going to jump, we're going to jump right back into our designer. I'm going to close these previous simulations. So we open up Designer and we create a new simulation. This particular one requires us to have silver defined. So we're going to go to the Profile Designer, which again is opened by double-clicking on Materials. And I'm going to import an XML file that I've previously created. And that is silver. So we create the silver in the dispersive. And again, just a note that for these Lorentz-Drude terms, in OptiFDTD 13.0.3, you have to do the fitting to come up with these coefficients, and you can enter them. You can specify however many resonances you want and just enter in these coefficients. In the upcoming release, you'll be able to actually load in a refractive index file, refractive index versus wavelength, and it will actually calculate these coefficients for you. So we're going to go ahead and close out. Nope, sorry. I'm going to change this waveguide. This is a default waveguide profile that gets created. We're just going to change the 2D. This is going to be a 2D simulation, and I want to specify the refractive index for that waveguide to be air. And we're going to store that, make sure our silver got stored, and then we close off our Profile Designer. Now we're going to go in and we're going to specify our simulation domain. This one's going to be a bit bigger, so, well, a bit more square. 1 micron long and 0.55 microns wide. It's a 2D simulation, and we want to specify the refractive index, and we want this background to be silver. So we specify that. It will change our simulation space. We're going to now start creating our components. The first one is going to be that primary waveguide that runs across the whole space. Open up our settings. We want it to run from 0 and be centered on 0. As per the paper, it's going to have a 50 nanometer width, which is this number right here. The waveguides, when they get created, they start with that default waveguide profile, which we changed to air, so that's fine. And I'm going to specify where I want it to end. I want it to end at the 1, and I want it to remain centered. So we're going to evaluate those, fix that to 0, and we're going to go ahead and hit OK, and now we have our first waveguide. The second one is actually going to be the tooth, that tooth in that profile that we created. So we're going to create another waveguide and set up its parameters. Its horizontal is going to be at 0.5. Its vertical is going to be 0.025. Now, we don't want it centered right on this origin. We want it on the surface of this original waveguide. The waveguide is 0.05 wide, so we need our vertical to be 0.025. We set our offset to 0, and we also fix our end to be at 0.5 in the horizontal. Now, here's our opportunity to start doing some parameters and parameter sweeps. We're going to run 2 simulations. One is just the waveguide, and then the second one is the waveguide with this tooth. So what I'm going to do is I'm going to define the vertical height of this to be 0.25 plus L, which is a parameter that I'm going to define. I want its width to be 0.05. Now, when I hit OK, as with the previous examples we've seen, it's going to recognize that there's an unknown variable. We hit yes, and we go ahead and create that variable. And I want it to be 0.1 microns tall, at least in this case. So we go ahead and create our profile. I want to make sure it got created. My offset was not set to 0. And now we have our profile. So what's going to happen is I'm going to set up a parameter sweep. In fact, I'll do that right now. We'll set up our parameter sweep so that we sweep across that L. So we're going to hit L. We're going to hit OK. Now there's two examples I want to run, one without the tooth and one with the tooth. So we're going to set iteration count to 2. And then we're going to assign these values. So the first run I'm going to put as 0.1. Second, actually I'm going to make it 0. And then the second one I'm going to make it 0.1. And then I'm going to hit OK. So what will happen is when we do our parameter sweep, the first time it'll set the height of this to be 0. And then the second time it'll run, it'll set it to the 100 nanometer height that we actually want. So that's those. Now we need to define our input plane. And we're going to go ahead and define it to be we want it to be located at 0.15. And with this particular one, we're actually going to show modal, because what we want to do is we want to inject a modal profile across this. So we're going to hit modal. We're going to go define 2D transverse. We want to find the modes of that particular waveguide. We're going to go to our parameters. We want to specify, we got to specify our operating wavelength before we do this. Find modes, and we're going to go to TM. We want to make sure there's enough sampling points to actually find the mode. And the other thing we're going to fix is the contour integral that's used for the actual mode solver. It takes a look at the refractive index in the complex space. So we want to define the real part. We know the real part runs from 0 to about 2, and we know the complex part runs, sorry, this is, yeah, that's the real part. This is the complex, 0.05, and we're going to run this one as -4. And we're just going to increase the tolerance a little bit, decrease the tolerance a little bit. And then what we're going to do is we're going to head and tell it to calculate the mode. It calculates the mode of the structure. And when I click it, it calculates that profile for the HY. We go ahead and hit apply data. And our mode is almost fully set up, our input plane, I mean. We want, again, it to be a pulse. So we're going to take a look at those pulse properties. And we're going to set up our full width half max to be actually pretty much these default values, but not quite. There we go. That's what we want. We're just making it just a bit wider than what we originally wanted. The default had it as. And then we're going to create 2 observations. The first one, which is the one we actually need, is the observation line. And we're going to put that at 0.9. with a length of 0.6. Nope, sorry, 0.55. And then we are going to also create an observation point at the same spot. And this is just something I always typically do, and it's so that I can take a look and see whether that power has decayed sufficiently for this particular simulation. Then what we can do is we can go to our 2D simulation. We can specify it as a sweep. We also want to make sure our resolution points are small enough. These ones are not. These are based off of the central wavelength. So what we're going to do is we're going to, if we just want 1 point across our waveguide, we'd be 0.05. We want at least 10. So we're going to do 0.005 for both these simulations. Then we're going to, as always, drop this just a little bit. And then we want to specify that this is a long enough time, again, for enough energy to run through. So we're going to specify the 9,000. And then we would go ahead and hit run. And this would run those 2 simulations. So I think this is actually a good point to stop for Brian to do the second poll. And we'll go ahead and run these, and we'll take a look at the results when we come back.
Okay, thanks, Scott. Second poll is now launched. There are a couple questions already in, but obviously we're taking as many questions that you guys can send at us. So feel free to type it in right now if you have anything that's on your mind. This is the last chance to have a one-on-one with Scott this week, and probably for webinars for at least a couple weeks. So please take the opportunity. And again, just to reiterate, all the videos are going to be available. We're going to make them available online on the page that you use to sign up. This video should be rendered and on there in about an hour from now. We're also going to clean up a lot of these videos and put them on YouTube with a little cleaner redub of the audio, so that we can get all the concise parts of the presentation and make something that's straight to the point. But we definitely appreciate everybody coming for these webinar sessions and listening along with our presenters and asking the questions that you guys have been asking on the topics of your interest. So there's quite a few questions. I'm trying to stall a little bit for Scott because a lot of them are pretty lengthy, but I'll go ahead and I hope you guys had a chance to read through the first couple at least, and I'll let him go ahead and answer you guys. Okay, Scott, take it away.
Thanks, Brian. A couple ones. I've got a question about when I was setting up the nanowire example. The question was, why did I use a fiber profile instead of using the 3D object? There's no real reason. It was a personal preference thing. I just happened to default to the fiber approach as opposed to going to using the cylinder from the 3D shapes. The other question I got was about whether the object should be touching the boundaries of the simulation space. And with the PML, what it will do is it will match the material that's approaching it. That's how the equations are actually set up. It will use the local refractive index at that edge, and it will match it so that you don't get reflections from it. There can be issues depending on what style of PML you use if you're using a metal, but in general, in terms of dielectrics and that it won't be a problem. The other question I had was in regards to specific materials and whether they are in our libraries or not. There is an extensive library that comes attached. So if I open up Designer, here, if I open up Designer, if we look at the materials library, if I right-click on the design and go import, there's actually a fairly extensive materials library that exists that's available for you to import. There's Sellmeyer fits. There's different crystals that are available. The one question I got specifically was about zinc oxide, and if it's not in our library, like I said, in 13.0, which is the current version of the OptiFDTD, if you do a fit to the Lorentz-Drude model and you know what those strengths are, those coefficients, you can actually create a new dispersive material. So if I go new material, I want dispersive, you can actually go into the Lorentz-Drude and you can specify what you want these coefficients to be. This is the strength, the plasma frequency, the resonance frequency, and then the damping constant. If you can do that fit, then you can use these coefficients. With the upcoming release, OptiFDTD will provide you the opportunity to simply load in a refractive index file. So for example, if you go to refractiveindex.info or websites of that nature, or you have experimental measurements relating the wavelength to the refractive index, we will actually be able to fit that and load it into the Lorentz-Drude model so that you can use it. So that's about it for those questions. If there's a couple others that I'm going to respond to directly, they're just easier in that format. But for now, we're going to go ahead and take a look at those results from that plasmonic waveguide example we did. And there's two ways of looking at it. So two files get created when you run that. This one here, which is the first one that gets run, and then this one here, which is the second one that gets run. You can look at them both independently if you really wanted to, but what I want to take a look at is I want to look at the results of both. I ran them for that reason. So I'm going to open up the last one, which is the 001, and it's the one with the tooth. And what we can do is if we go to Tools, we go to Parameter Sweep Analysis, that will give us an opportunity to take a look at all of the results together from this particular parameter sweep. So if we go to Power Spectrum on observation line 1, there's only that one observation line. Here's the results from the first simulation where the length was set to 0. So we take a look at the transmission, it starts going off to 1 as you get to higher and higher wavelengths. If we take a look at with the tooth, we can actually see the transmission characteristics of this particular plasmonic waveguide. So if we pop back to the presentation, we can see here are the OptiFDTD results on the left, and we can see the results from the paper on the right. Now there is some difference in terms of what the maximum transmittance is between ours and theirs. There's a number of reasons for that, one being the resolution sizes that were chosen, the lengths of simulation, but the other issue is that the results from this paper, we're using a Drude model, we're using the Lorentz Drude, so we're actually modeling slightly different materials with different properties. They're both silver, but are over different wavelength regions and that. But we do have the general transmittance results for that. The final thing we're going to take a look at today is a question we've gotten from a number of people over the webinar series, and that's how can we do non-uniform meshes? How does OptiFDTD implement that? And the way we do it is you define a specific region in which you want to run your higher resolution across your axis, and we actually scale from the larger radius down to the one larger mesh down to the one you want over that region. So what I mean by that is we've specified a large step size in X in general for this particular one, but once we hit 0.1, we want to be running a much higher resolution. Well, between about 0.2 and that 0.1, we actually step down to it, so it's not an abrupt jump from the large mesh size to the smaller mesh size. And that can be done in X, Y, and Z. So we're going to go ahead and take a look at an example. We're not going to run the simulation for it. I can show the results, but even with uniform meshing, it's a long range. It takes a long time to run. So we're going to hop into the designer, and the example we're going to load in is this one right here. So in this particular design, what we have is we're running a simulation over a domain, and it's a 3D simulation, over 0.8 microns in length, 0.7 microns in width, and based on the 3D wafer parameters, it's 0.7 microns in Z. So if we take a look in the 3D editor, which is one of the tabs down along here, we can see that we're modeling a fairly small sphere in a fairly, I wouldn't say a large space, but a relatively large space compared to the size of the sphere. And if you were to try and run your simulations over the resolution for this sphere, over the entire space, you would be looking at a very extensive simulation that would take a very long time to do. So I'm just going to take a look at some of the specs of the simulation just to give you a framework for understanding why we would want to do this. So if we take a look at that sphere, it actually has a radius of 0.05 microns or 50 nanometers. But we are actually running a simulation space that's about 10 times larger than this radius. So if we were to try and run a simulation that meshed this radius, which you would want 0.005 at a minimum, so 10 points across the radius of the sphere, you'd be running 100 times larger than you would need over the simulation space, which we want trying to avoid. So the way to get around that is by going into the 3D simulation window. And under there, we have a section called non-uniform mesh parameters. If you uncheck it, it will just run with the X, Y, and Z mesh sizes that you want, that you just define. Now, if you want to run something higher, you want to use this uniform mesh, and then we're going to go take a look at those parameters. So there's a tab for each direction, an X, a Y, and a Z. And what you're going to do is you're going to define the maximum and then the minimum. Okay, and what we're doing with that is the maximum will be what you want that mesh size to be. What you want, that should be 0.5. We don't want to run. So we're going to run with the auto on our X, Y, and Z, which is 0.05, which is good for your wavelength that you're using. But under our mesh, we have a maximum and a minimum. And so what's going to happen is over the entire, actually I'm just going to pop this up so we can take a look at it here. This is a graph of that mesh that you're going to be looking at. Over on the outer edges, we're going to be running with that 0.05 micron step size, which is fine. That's all you need out there. There is no structure there. This sphere is centered at the center of the simulation domain, so there's nothing here. So we can run with resolutions that are just big enough for the source. Once you hit the region that you want, so in this context, we've specified we want the fine mesh, the 0.005, to start at negative 0.08 and run to 0.08. So we want in this range here, we want it to be that superfine mesh. And then the maximum mesh size is what lets you govern this gradient. So we've gone ahead and defined a region for the X, which runs around the center. We've defined a direction in the Y that runs, I'm going to move this around a bit. Let me move this so we can actually see the whole space. There we go. And parameters. So again, the X is run through the center, so it's on either side of this. We take a look at the Y. Again, it's running from about 0.27 up to 4.3, so on either side of the sphere. And then the Z, again, is run on either side of the sphere. And every one of these is designed to give us a large mesh size out on the edge, but a very fine mesh size over the period of the sphere itself. So this will let you actually truncate the number of spatial steps that are required to actually calculate this simulation to a converged result. The other thing to keep in mind is your step size that gets calculated, it will actually adjust to this non-uniform mesh and to ensure stability of the simulation. So you don't actually need to worry about maintaining that stability criterion that's required for any FDTD simulation. So if we were to run this, and I'm not going to do that because it'll take longer than fits within a webinar format. If we take a look at that result, we get our observation area, our observation point. Again, we take a look at the point to make sure the power has decayed sufficiently, and then we can take a look at the power spectrum from this observation area. We want to look at all of the power that's propagating in the Z, and sure, we're looking at the absolute and that it's normalized to the input plane, and we can actually see this reflection that occurs at just above 0.5 microns for this particular design. So that's actually all we wanted to do to wrap up the OptiFDTD webinar series. It gives a certain sense. The previous ones gave us a really good sense of the tutorial of how to do it, and we wanted to wrap things up by showing a few more advanced examples that addressed some of the questions customers had about the capabilities of the OptiFDTD software. So I'm going to hand it back to Brian, who will wrap up the webinar for us.
Okay, thanks, Scott, and thank you all again for attending these sessions during our webinar week. I hope everybody has learned something useful about our product features and their capabilities. And I'd also like to thank Scott and our other presenters for the terrific work they've done during this week. We do have a couple questions still coming in, so I'm going to pass the mic back to Scott. But otherwise, I hope everybody has a great weekend. And if you'd like to email us about suggestions for future webinars, please do so. Okay, back to you, Scott.
Thanks, Brian. The first question we got is in regards to, I'll actually open it up, is in regards to the plasmonics example we did, which is this one here. And what I did was I basically sat this tooth up on top of the waveguide so that there was, I chose my sizes so that in the layout, these are the same. So this one was centered, this one had a wavelength of, sorry, not a wavelength, a width of 0.05 and was centered at 0, which means this edge was at 0.025. I specified I wanted this one to be located at 0.025. So the concern was, does special care need to be taken that both of these will always be touching? And the answer to that is that if they're both defined as the same point in the layout, when they get discretized, they both will be at the same point. They may not actually both be at exactly 0.025 due to discretization issues like we've seen before. So if we take a look in here, if I zoom in on this, so this particular line right here may not be at 0.025. It might be a little rounded up and down. But these two together will always be at the same point. They'll be discretized at the same point. So you don't need to worry about it in that sense, that, you know, if I choose a different grid, these may not be touching. But when you're doing the layout, you should make sure they are touching. And the one piece of advice I would give is if there's ever any concern with the layout, I strongly encourage people to check out the 2D or the 3D refractive index tabs. What you see when you click on this is the mesh. So there is no question about whether this, what's being simulated versus what you're looking at. This is the mesh, and you will see this change, particularly with round structures, as you change your mesh size. So that's what I'm going to say about the design of this particular structure. The other question I've got is, does negative power always refer to reflectance? And I'm going to be very cautious in how that gets interpreted. So if we open up the non-uniform mesh example, the results from that, and we take a look at the, no, this one won't show reflectance. Let us just take a look at, actually, we'll look at the plasmonics one. Nope, my apologies, it is the rod one. I needed a simulation that actually has reflectance in it. So if we take a look at this one, we have two observation planes. We have the one that's located on the right, and we have the one that's located on the left. Now, in this particular example, when we took a look at the one that's on the left, which is observation area 2, when we look at the power, we notice that it's negative. The reason I'm saying that is reflectance is because what the negative is saying is it's saying that the power is going from the right to the left side of this particular observation area. So if I go back to layout, what I mean is if power being measured, how about we take a look at a bit more zoomed in here. What I mean is if the power measured on this observation area is negative, it means the power is going this way from right to left. If it's positive, it means it's obviously going from left to right. In this particular example, because of where it's placed versus the source versus the rod, yes, if any power is coming back through here, then you have reflectance. So the reason it's reflectance is because it's negative, it gives me the direction of the power relative to the observation line, but also because of the placement of the observation line. So hopefully that answers those were the two primary questions that came in for the second half. And I'm going to leave it there. And if your question wasn't answered, it's because I'm going to be addressing it with you directly over email because it requires a bit more of an elaborate discussion. And I'll send it back to Brian. Oh, before I do, I'd just like to thank everybody, again, reiterate what Brian's saying. Thank everybody for coming out. It's been a really rewarding week presenting all this to everybody. and we'd like to thank you for coming out.
Okay, thanks, Scott. I think that's a wrap, everybody. So thank you all for coming, and enjoy the weekend. Have a good day.